All right, so these are the topics which we covered in this course. We talked about linear algebra, which was required for some of the concepts in classical computer vision and also like deep learning. We have covered image filtering, edge detection, feature extraction. We learned like what neural networks are. We covered the basics there. Then we also studied autoencoders, then used CNN for classification and also like some linear classification, the classical way of doing machine learning. Then we looked into object detection, image segmentation, semantic segmentation, instance segmentation. Then we looked into how we can compute optical flow for videos. And in the last lecture, I think we covered action recognition. So those are all the topics which we covered. And I think it's a very good comprehensive list for a computer vision course. And I'm happy that we were able to cover all these topics. And today we are going to talk about camera modeling. And this is actually a very interesting topic, which we usually used to cover like at the beginning of the course, but this time we actually tried to restructure the course, try to bring in more of the deep learning because that's where the research field is going. And camera modeling, it was like quite different from the other topics. There wasn't any correlation, but still I think it's a very important topic. And I mean, there are like independent courses which just talk about camera modeling. So it's not like something which we can cover in one lecture. I think we used to have 2 or 3 lectures for this, but I'm trying to just give you an overview like what camera modeling is and how it's important for computer vision, so that you have a fair idea about that. Okay, so let's cover that. And so before going into camera modeling, let's try to understand like how image is formed using your cameras. You have any object in your 3D environment, in your 3D world, right? And then you have let's say a film here where you try to project this object from 3D space to this 2D space, right? So what happens is when light travels from the points on this object to this film, so some projection is formed. And here in this case, I mean, if you don't have any barrier in between, what will happen is for each point you will have multiple projections, and the image which will be generated will be kind of very blurry. So what we do in images is let's try to understand like the basic structure of a camera, which is like a pinhole camera, which was invented like long ago. So what we do is instead of directly trying to project the object in the film, we have a barrier in between, and it helps in like reducing the blur because each point was getting projected on multiple locations in this film. And in this barrier, we have the small opening, which is called aperture. And then what happens is it will try to block many of the rays, the light rays, from falling on this or projecting, which you're trying to project on this film, and it will only allow certain of the rays. So here you can see that for this particular point in this 3D world, this ray is trying to project at this location, and similarly for this, it's trying to project here, and it's trying to block all the other rays. So it helps in reducing the blur when the image is formed. And one thing you can observe is that your object is projected in an inverted shape, right? Because the top row is going down and the bottom ray will go up. So your object is inverted. So it's a basic structure of how your camera works. And it's not something new. So this is an image like from 1558. So this basic principle of this pinhole camera was known to Mosin for 473 BC. So that's pretty old. And I think Leonardo da Vinci, he has he used to use like for his drawings, right? He used to do painting, so this was known to him as well. So it's not something new. Now let's see what happens when we try to change the size of the aperture. So this 2 mm, it's telling you like how big your aperture is. So if it's 2 mm, that's the impression you're getting, that's the projection. And if you try to reduce your aperture, you can see that your contrast is improving, and the blur or all the distortions you have in these projections, it's gone. Okay, so we can try to reduce it further, but the issue will be the rays will try to diffract, and again the quality will go bad. Okay, so there is some like optimal amount of light you need to project your objects into your image frame. Now, instead of just an aperture, what we have is we have a lens, and again we'll have aperture will have a small opening here through which the rays can pass through. And the idea here is what will happen is when you have a lens, rays passing through this lens will be projected on this film. And from your high school physics, you might know that each lens has a focal length, which means that when a ray is coming from infinity, that ray will be projected in that location, and the distance between that location or that point and the center of the cell, that's called the focal length of the lens. All right, so it means that only specific objects in your 3D environment will have very good focus when they are projected into the film. Okay, and that's the location where your film is placed after your lens to get the projection of your object in the 3D world. So that's fine. Now that's the focal point where rays coming from infinity will converge. That's we discussed, and this distance is called a focal length. And of course, we have this aperture. We don't allow like a lot of rays to pass through, and this d is called like the diameter of this aperture. So it controls like how much light is coming through this lens, which will make the projection. Okay, so ideally we assume that our lens is very thin, but actually it's not true. So when we have this thin lens assumption, which means that it doesn't have any thickness, but ideally when your lens will have some kind of thickness, right? So in your normal cameras like which you use these days, it's not just one lens, you have combination of series of lenses which try to improve the quality of projection you get uh, after the rays are passing through the sequence of lenses. So earlier you saw like one image where the rays were actually coming from a point. They were projecting not at a single point, but like at a region, at a radius. So that was the blurry region where it will be projected. So to improve that, if you have a series of lenses, so each point in this 3D environment will be projected to one point in your film. So it tries to improve the quality of your projection. Another important concept in this projection is a depth of field. And depth of field means if you are into photography, then you might know that it tells you how much of the region in your image will be in focus. So you can see here that the depth of field is pretty low because the background is all blurry. You just have focus on the on these flowers. So this distance in the 3D environment, which tells you like all the objects present in that region, if they are in focus, so that defines the depth of field. If your depth of field is high, then this distance will be pretty large. Probably, I think I should have image for that here. So if your depth of field is large, then all the objects in this range will be in focus. So you can see the difference here. This is like very small depth of field, and this is a very large depth of field because the background objects are also in focus. I mean, not that great focus, but still better than the previous image. And this depth of field is controlled by the aperture. If your aperture is too big, then your depth of field will be very small. But if your aperture will be very small, you're going to have a very high depth of field. Okay. Now the human eye, it also functions very similar to a pinhole camera, and the film where the rays actually project the 3D environment, it's called the retina, and I think we discussed this in the first or the second lecture, that we have photoreceptor cells called rods and cones in a retina, which actually do the actual projection, right? Which allows us to see. And again, so you have a lens here, which actually changes its aperture, and tries to control how much light can come inside and project in the retina. And if you go outside in the sun, then you can see that what will happen is your aperture will, your lens will try to reduce the aperture here. Okay, so this pupil tries to control that. And if you come into the dark, then you can see that you will have very wide eyes because your aperture grows, because it needs more light to actually to see what's there in the dark. Now, so let's try to understand like how this pinhole camera works, some more details about this. So that's the pinhole from where the light is coming. That's your 3D object, your 3D environment, where the actual objects are located. And that's called image plane, or the film where a projection is formed of the 3D object, right? And this is the focal length. So you will put your film or the image plane at a distance of focal length from your pinhole. So this is again showing a virtual image plane. It's nothing, it's just like a replica of this image plane on the right hand side. All right, because on the left hand side, you will, if you try to visualize, it's going to be inverted. If this is a candle here, it's an inverted candle. But if you try to visualize in the virtual plane, you can see the same object, like the same orientation. Okay, so it's the same image plane here. We call it virtual because we are just trying to show it in the same orientation. Now, one important thing here is the 3D object here, which is in the real world, it's actually in three-dimensional world, right? It will have height, width, also as well as depth. So it's a 3D structure, but in the image plane, what's going to happen is you're trying to project this 3D object into 2D plane. So the depth or the Z dimension will be lost, and we'll see like how this 3D object projects on this image plane. And that's where like this camera calibration and this camera modeling come into picture. Okay, so the idea is if you have a 3D model of an object, so your object's in 3D world, right? What you want to do is if you have the image, which is like the 2D projection, right? Your projection on this image plane, what we have to do is we have to determine the location and orientation of object. So we want to know that where this 3D object is actually located and what is its orientation. And by orientation, we mean like the translation and rotation with respect to like your image plane. And if we know that translation and rotation, then we can use that translation rotation to actually project this 3D object into any any 2D plane, image plane. And if we have determined the exact, the actual translation rotation, then the projection should be exactly same as the projection of this object on this image plane, right? So the whole idea is we have to determine these parameters, the location and this orientation, to actually know how this 3D object is being projected into this 2D plane, right? So now one will ask like why exactly we need that. So let me try to motivate you and give you some example where this is used. So for example, so this is a very classical example where we have to insert some objects like in any scene. It could be just an image, it could be any video as well. So here we are showing an image insertion. So if we have this object here, and if we know the translation rotation of this object or the orientation of this object in 3D world, right? Then what we can do is we can use that information and we can again project the same object in a new image. For example, in this case, the second image here. All right. So you can see here, we have tried to project it here. And so that's one application. And here you can see that we can also add like a shadow, which is consistent with this target image. So it's not realistic, but if you would have inserted the right object, it would have been a realistic image as well, right? So that's one application where it is used. Another interesting application is in robotics. So in robotics, what we need is your robot has to do a lot of automation, right? A lot of tasks which we as a human can do. And to do that, the only knowledge robot can have is like some cameras. And cameras, as you saw, like they are projection of 3D environment to a 2D plane. So then in the 2D plane, you have lost like the actual structural information of all the objects which are being projected. So just by just looking at the image, it will be very hard for the robot to perform the task. So what we can do here is, so let's say we have some images of some of these objects, right? We can detect those images. You know how to do object detection. And after we have detected the objects, if we have multiple views of the same images, what we can try to do is we can try to do a 3D reconstruction of these objects. And once we have that, so then it's not just the planar 2D image. We have the complete 3D environment information here. All right. And once you have that, then it's very easy for the robot to actually do the task, because it's not just like the 2D projection the robot is seeing. He actually knows like what's the depth of the scene where the object is actually located. So he has the complete 3D structure. And once he has that, then it's very trivial to actually pick up all those objects. So it's just picking objects in this case, but it could be anything else as well. So it could be useful for maybe your self-driving cars, because once you have the depth information, then it will be easy for the car to actually perceive, or whatever algorithm it's using to drive, to perceive what's there in the scene. Okay, so that was another application where this is used. Now, before we proceed, like how we can do that transformation, or how we can estimate those parameters, which actually helps us in projecting the 3D environment to the 2D plane, let's try to understand like the coordinate system. So in this case, this is your 3D environment, 3D world, and a point here. And these are your world coordinates, capital X, Y, Z. All right. So location of this point in world coordinates. And this is your camera center. All right. So again, this can be your camera coordinates, and it's different from your world coordinate. And then you have your image frame. So in your image frame, you can also see that you have a center, and you will have this X and Y coordinates. So this line over here, this is called optical axis. All right, passing through your camera center, passing through your image center, and it could pass like anywhere in the 3D world. And this point P, which has a coordinate of XYZ, capital XYZ, in the real world, if you project that in the image frame, it has a coordinate of X and Y. Right? So the small x, small y is the coordinate system in your image frame, and this capital XYZ is in world coordinates. So these two are different. So try to understand that. Now, okay, so yeah, we covered the center of projection, that's fine. And this image plane is also called projection plane. And we have put it like in front of your camera. So that's easy to visualize. Ideally, it will be on back of your camera. So here you can see that then the coordinate of this projection, this projected point will be this X bar, Y bar, and a negative D. So D is this distance from the camera center. It's negative D because the actual image is actually formed on the other side. All right. Now let's try to understand like some of the issues which we can face when we are projecting a 3D object into a 2D plane. So the first issue is the appearance of any object. So you might know that if an object is far away from the camera, the actual projection size of that object will be much smaller when you compare that with the object which is actually closer to your camera. So in real 3D world, the size of both these objects are similar, right? It could be the same person. But when you're projecting this into the image, you can see that it's pretty small here when you compare this with this person in the front here. Now, that's problematic because actually the objects were of same size. But then how will you infer that these are the same objects or not? Because the sizes are totally different, right? So that's one issue. So the other issue, okay, so all the points which you have in your 3D environment, they will form points in your projection in the image frame, okay? And all the lines which you have in your 3D environment, most of the times they will form lines. But if they're along the optical axis, then they may also form points. All right. So that's just a special condition. And if you have planes in your real world, they will also form planes in your projected image, sometimes just half planes. And polygons will go to polygons. So these are like just general projection rules. Now, some of the interesting facts here, if you have parallel lines in your 3D world, something like this. So this is your actual 3D world, all right? And you can see that these are parallel lines on the ground and maybe on the wall. And these are three different objects here, same size, exactly same height and same shape. So in the 3D world, you know that, but when you will try to project this into the image frame, what will happen is your parallel lines will try to merge at infinity. So that's called vanishing point. So they will not like appear parallel. And your objects, as we discussed, if the objects are further away from the camera, they will tend to appear shorter. All right, so that's the projected view. This was the actual 3D environment view. Okay. Now, sometimes this can be useful as well, and I think that's in the next slide. I will talk about that. So in this case, you can see this is a projected image, and you can see like the difference in height, and it can easily fool you that this is like much smaller than this lady here. But actually, if I show you how this photograph was captured, so this is the camera setting. The camera was at this location, and this lady was standing here, and this lady over here. All right. So you can see that even though they have the same appearance or the same size, but what will happen is the actual perceived size will be what what we are seeing in this perceived wall. So the rays coming from here, you can see if they just pass through this object, they grow much bigger when they go to the perceived wall, at the image frame, right? And that's the size of the radius. So if the object is that small at this location, the actual projection will be this big. But this lady over here, she was already like close to the perceived wall. So the size which we are seeing might be the actual size. And that's the reason you are seeing like this much disparity here. Okay. Now, this, I mean, sometimes this can be very useful as well. So I think all of you might have seen this LOTR movie, Lord of the Rings. It's a nice movie. And in this movie, you might notice that this person is like much smaller as compared to this Gandalf here, right? So in real life, I think the height of this actor, Elijah Wood, is 5'6", and his Ian McKellen is 5'11". So it's not that of a big difference, right? But in the whole movie, if you observe, he was like a dwarf, and this is a very tall man. So I think what these guys did is they tried to use the idea of this projection, like how your perceived objects can be much bigger when they're close to a camera. And it wasn't that simple. And I think they try to use multiple cameras. So I think they put like one camera very close to Gandalf and then one common camera to shoot the full scene. And later I think it was merged with the later scene. So it was not that trivial, but the same idea was utilized. Okay. So I think that was enough to motivate you why we need to study this camera modeling and projection of 3D world to 2D world. So it's not just important to understand how the projection happens, but it has a lot of applications as well. Now let's try to go deeper into like these coordinate systems. So this is your 3D world, and your coordinate system is capital XYZ. So that's the location of this point. And this is the image plane projection of the same point. Now, from your basic mathematics, I think your high school maths, you would have learned that if you have similar triangles, then if you take ratio of their sides, it's equal. So these two triangles are similar, right? Because the angles, this is a right angle, again, this is a right angle, and these opposite angles are equal. Then we have this equality. We can say that this negative of y, because it's inverted, over f, all right, the ratio of these two sides should be equal to ratio of these two sides, these two sides. So y over this z, right? So that's the equality. Now this gives you the value of this coordinate y, and it will be, if you take f to the right hand side and the negative sign on the right hand side, it will become negative f y over z. Similarly, you can get x equals to negative f x over z, right? So these xy are coordinates in this image frame, and you can represent them using the world coordinates xyz. Okay, so now that was one way where you were assuming that your origin is at a length center at this location. And there are other variations as well, where you can assume that your length center, your origin is not at the length center, but at the image plane. And if you do that, again, you can use the same identity here, but instead of z in the denominator, this time you will get z minus f, because your origin is this location, and you will have to take this distance, then it will be this whole z negative of this f, all right? But it's the same equation. It's just like where you are placing your origin. Now, one thing you might observe here is that this transformation is actually not linear. And the reason for that is you have a z on your denominator, and the z is not a constant. The z is going to change with every point in your 3D world. All right, so therefore this transformation is not linear. So what we can do is we can try to convert these coordinates into homogeneous coordinates. And you have learned this trick earlier as well, I think, in second or third lecture, where we're trying to understand how we can do rotation and translation. So similar to that, you add a extra coordinate here. It becomes xy1, and this is your homogeneous scene coordinates. You have xyz, and you have three coordinates for 3D environment because it's 3D world, and this is the projection. It just have two dimensions. That's why it's xy1. All right. Now what you can do is, if you have the homogeneous coordinates, you can go back from your homogeneous coordinates to your normal coordinates. And the easy way to do that will be, you can just divide your xy values with the third value here. So that will give you x over w here, y over w. And similarly for your scene coordinates, you can divide all the coordinates with the fourth element here. So in this case, it was just 1. So if you divide by 1, it doesn't matter. You will get the same coordinates. But if it has some number, you can just divide with that. Okay. So that was some minor detail. Now let's try to understand how you can project like your 3D point onto your image plane. So you can represent that projection using a matrix. So I will go through this, how you come up with this matrix. So let's say you have this projection matrix, and these are your 3D world coordinates, and you want to compute your coordinates for the projected image. So if you solve this equation, you will get a column vector, right? So x will be multiplied by 1, y will be again 1, z with this, right? 1 with 0, and rest of the elements are 0. So this will give you x, y, and negative z by d. Now, if you try to get the coordinates back from this homogeneous coordinates, as I told you, you can just divide these values with the third element, all right? And that will give you x over, so z, z will go in the denominator and d will go in the numerator, you have the negative sign, right? And these are the exact same coordinates which we just saw in the previous slide using the property of the similar triangles. All right. So this is called perspective projection, and this matrix is called projection matrix. And what it's trying to do is it's trying to convert your point in 3D world or 3D environment to the point in your image frame. All right. Now let's go through a couple of examples. So let's say you have a 3D point located at 10, 6, and 4, and let's say you have a focal length of 2. Right. So this is a point in your 3D environment, and so your focal length is 2. So this d will be 2. You can just replace the values here, and when you will solve this, this will give you 10, 6, and -2. I think it's pretty simple. You can do that. And to get the coordinates back, you know you will have to divide these numbers with the third term. So that will give you -5 and -3. Okay, so 10 divided by -2, that will -5, and 6 divided by -2 will give you -3. Right? So this means what this operation is trying to do is you have a point in your 3D environment at a location 10, 6, and 4. Right? So that's the world coordinates. And what you want to know is that if that point get projected to an image frame through a lens which has a focal length of 2, what will be the exact coordinates for that projection? So this projection matrix is giving exactly that. So it will be -5 and -3. So let's see another example. You have another point 25, 15, and 10, and again the same focal length. And if you will solve this, you will again get the same coordinates, -5 and -3. So what does this mean? This means that your projection, this perspective projection, does not have a one-to-one mapping. All right, so multiple points can actually be projected to the same point. And if you try to understand this, so try to visualize this, because in your 3D environment, if you have multiple points, like just like maybe following the optical line, all those points will be projected to the center of the image, right? And similarly, if you have points which are off the optical axis, but they might get projected to the same point in the image, and depending upon like what's the focal length and what is the aperture, right? So it's not a one-to-one mapping. And that's why what happens is, so in your 2D images, you know that if you're seeing for so at any pixel, it tells you like which object is present, right? And you know that there might be other objects present in the same pixel location which are hidden by that object. So that's another way to understand this. So all those objects are actually getting projected to the same pixel location, but the one which is actually closer to the camera will only be shown in the 2D projection. Okay, so it's not a one-to-one mapping. And this is also fine. Like if you just scale your projection matrix, so you multiply this by d, then again your projection is not going to change. Okay. So if you multiply this matrix with d, so these will be -d, and this will become 1. And again, if you solve this equation, you will get the same coordinates. So your projection is not going to change if you just scale your projection matrix. All right, so I think this we have already covered. Let me try to wrap up this quickly. So parallel lines, we know that they might not be projected parallel in the formed image. And here you can see that although like these lines here, they are parallel in the real world, but in the image you can see that they are kind of merging together. And this point actually where these parallel line merge, this is called vanishing point. And again, angles, you will observe that even though if you have, let's say 90 degrees in the real world, so all these are 90-degree angles, right? But when they're projected onto the image, they might not be 90 degrees. Right? So it's, I think, more evident in this third image here. So these corners should be 90 degrees, but here you can see that, I mean, this seems like maybe 40 or 45 degrees, right? And again, distances, they can be deceiving. I mean, the distance here, you can see that the distance between these 2 points here, okay, it's equal to like distance between these 2 points. But after projection, that's not the case. These are like pretty shorter as compared to this one. So if it's farther away from the camera, they will appear very small. Now, an interesting question is then how many numbers actually we need to describe a camera or its position to actually estimate the projection. So the first thing is we need to describe its pose in the world. So by pose, we mean like where exactly the camera is located, the XYZ values, all right? And also it includes the orientation, where actually the camera is pointing, to which direction it's pointing. So that includes pose. And we also need to describe its internal parameters. So internal parameter, you saw that such as like the focal length, which will define like where exactly your images will be projected and what will be the actual coordinates. So we have these two things, which I think we can represent in a form of a matrix. So basically we have two coordinate systems. The first is the world. It's a real world where we live in, and we can define like any origin. It's up to us. And then based on that origin, each point in this 3D world will have a location which will be defined by XYZ. Okay. Then the second coordinate system is the camera coordinate system, where the origin is the center of the lens, all right, and then it has its own coordinate system. Here we are describing that with small xyz. Okay, so we call this world coordinate system and camera coordinate system. Now, so let's go back to camera parameters. Uh, so what we want to do is we want to project a point in the real world, which can be XYZ, into the camera. Okay, so for this, what we'll have to do is first we'll have to transform this point XYZ into camera coordinates. Okay, and this you know from I think second or third lecture where we're trying to learn how we can rotate and how we can do translation using homogeneous matrix or homogeneous system. So it's exactly the same thing. So we have to project a world from 3D world to the camera coordinates. And for this, we need to know like what's the pose of this camera or the position of this camera, where it's located in the actual world, and also its orientation, at which angle it's placed. If we know that, then we can use rotation actually to fix the orientation, and we can use translation to actually fix the camera position and move from world coordinates to the camera coordinates. Now, once we have that, then we are in the camera coordinate world. Then we just need to find the projection, and all we need is camera intrinsics. All right. So these are all the things which we need to move from like a 3D world, how it's getting projected into a 2D plane. And these two things, we actually separate these two. These are called intrinsic parameters, which are specific to a camera. And these are called extrinsic parameters, which define like the location of the camera and the pose of the camera. All right, so you can define any camera with the translation, right? And the rotation. These two are extrinsic parameters. And then the intrinsics are focal length, the principal point, and the pixel size. So now that's your world coordinate. And let's say this is your projection matrix. This projection will give you the coordinates in the image frame. So we need to find out this matrix. All right, let's define that using this bigger pie. And this pie can be actually broken down into these four matrices. So the first matrix is the intrinsics, which we also saw like earlier, the perspective projection, right? So these intrinsics have these focal length negative f here, and this is like translation. This translation is required like if your pixels are actually not squared, they don't have equal height and width. Okay, and again, so these parameters are not standardized. I mean, you will find different meanings or different representations of these in different books, but the basic idea remains the same. You have intrinsics and extrinsics. All right. Now, so let's start from the beginning where you have a camera in the 3D world at this location. And this is your origin of your 3D world coordinate. And this is the orientation or pose of your camera. Now, the first step, as you know, is like translation. We'll have to move the origin of the camera to the origin of the world coordinate. All right. So in this case, if the location of this camera is, let's say W, V, and U, and let's say this distance is C, so we'll have to translate this by this value C. Okay. And once we have the translation, the camera will be located at the origin of the world coordinate. All right. And you know that how we represent a translation as a matrix. We covered that in the second or the third lecture, right? You have these translated coordinates over here. So it will be a column vector. And this is like a square 3x3 matrix, identity matrix, because the diagonal actually represents the rotation, and I think the off diagonal values represent the skewness. We don't need any of those, so therefore we are using identity matrix. So that's your translation matrix. Now the second step will be we want to rotate this camera, right? So it just points along this z-axis, that optical axis. Okay. So again, we can just use a rotation matrix for that. And you know that you can define a rotation matrix using a 3x3 matrix. And that will rotate the camera. So that's the first two steps which can be done using extrinsic parameters if you know the pose of the camera. All right. Now the next step will be how we actually project this 3D point or any 3D point on the image frame, and for that we need intrinsic parameters. So we already covered that. We can do that using perspective projection. That's the matrix we use. All right. But this is like very basic matrix. A more general form is something like this, where you can have a different focal length in X and Y direction. So it could be like fx and fy as well. In this case, we are just showing f. And oh yeah, so we have the aspect ratio. So it's taking care of that. S is showing like the skewness. All right. And Cx and Cy here are actually showing the offset like of the principal point if it's not actually intersecting with the plane at the origin, right? So these are the intrinsic parameters. So it's like a more general form of this perspective projection, which we discussed earlier. Now, this focal length, let's try to understand what this focal length does. So if we increase the focal length, it actually tries to act like as a zooming factor. So if you increase the focal length, you can see that these two images of the same scene, this one has a higher focal length. So it's a more zoomed in version. And again, the second image, so I think this is using a telescopic lens because it's looking way too far. I think it's the same mountain over here. Yeah. So again, if you increase the focal length, okay. And also like if you are zooming in, you're also reducing your field of view. So it's a trade-off between these two. And finally, that's the full projection matrix. This is the translation. The first step, that's the rotation. And all of this is extrinsic parameters. That's the normal projection. And these are the intrinsic parameters, where again, you can define them using a matrix. Okay, so you have a point in real world, in world coordinate, XYZ1, and the goal is to project this into this image coordinates. So if you multiply with this projection matrix pi over here, that's exactly what you will get. All right. Now, let's see, we still have some time. So those were like the basics, but of course, that's not exactly how it's being done. We have lots of other difficulties there. We have many distortions. So normally we assume that we won't have any distortion. So that will be your projected image. But actually what will happen is you will in the real world, like if you do that projection, there will be many distortions. So this is called barrel distortion, and this is called pincushion. And you can see here that even though these are parallel lines and they should have been parallel, but that's what happened. And sometimes it's like it's due to the imperfect lenses. And sometimes it happens if you are using like maybe a telescopic lens, that also causes such aberrations. So this is again showing a radial distortion. So if you have to correct that, that's like the actual image which you want. Okay. So now one big question is, okay, that's fine. We have the projection matrix, but how can we estimate that matrix? And that's called camera calibration. And usually what we do is we use very simple images like this checkerboard images, and then we can place these images in the real world and take photographs. And the good thing about that is you can easily estimate like the distance between different points in these projected images, in the projected image as well as in the real world. So this is like a very basic method which is used for camera calibration and which helps you in identifying all those matrices which we just covered. So we are not going to go into detail because it's again like as I said, I think even just talking about camera calibration is going to take one lecture. So, but that's just the intuition and the basic idea behind it. All right, so that's all from my side. If you have any questions, please go ahead. So I hope your course project is going all right. Some of you had questions, so it's good you came to the office hours. I think that's always good because it's better to discuss than to just get stuck. All right. And so today was like the last office hours, but of course, like if you have more questions and if you need any help and if you have any concerns, just write us an email. And if you want to meet, that's also fine. We can arrange a meeting. All right. So next week we won't have any office hours, and this was the last lecture. We'll just meet like for the final presentations on 10th. Okay. So if there are no questions, then maybe we should end it here. All right. Bye. Have a good day.
Have a good day too.